Yeah, good morning. So today let us start with the final last topic which is pending in module 3, that is with respect to solar energy. So in this we have construction working and application advantages and disadvantages of photovoltaic cell, as well as we have a procedure like how to synthesize solar grade silicon using Union Carbide method. So these two are pending. So before going into the construction and working of a photovoltaic cell, let us know what are the photovoltaic cells. So we know that solar energy is such a huge resource for all of us on this earth, because without it we cannot imagine life to be possible on this earth. Okay, and using the solar energy, one of the best invention I can say, that is in the form of this photovoltaic cell. So what is a photovoltaic cell? Photovoltaic cells are called as solar cells, and these are the semiconductor devices in which sunlight can be directly converted into electricity. Photovoltaic cells are the semiconductor devices in which sunlight can be directly converted into electricity. So, as long as light is falling or shining on the solar cell, PV cell will generate electrical energy or electrical power. And when light stops, electricity stops. Okay, so as long as the light is falling, as long as it is cloud free environment, we can generate electric power. Whereas when it is cloudy in nature or when the light stops falling on it, electricity stops. Okay, uh, so these are made up of semiconducting materials, and the material which is used in these solar cells is a semiconductor material called as silicon. Okay, so with this introduction, let us go for construction and working of a photovoltaic cell. If you find like my connection is unstable, please let me know, because from yesterday I'm facing severe internet issue. Okay, so please let me know if my voice is not clear or if it stops in between in the chat box, so that I'll come to know whether I'm audible or not. Okay. So construction and working of photovoltaic cell, it will be asked for 6 marks. One of the important question for this, we need to draw this diagram, a very simple diagram. It's construction and working. Okay, so this has to be written. So first, let us understand what is this diagram. So this photovoltaic cell, it is made up of an ultra thin N type, that is phosphorus doped silicon. This is N-type phosphorus doped silicon. Below it, we have a thicker layer of boron doped P-type silicon. So N-type silicon is on the top. Below it, we have a boron doped P-type silicon. When these two are sandwiched with each other, there develops a junction called as PN junction. So this is the depletion layer, I can say. So this is the PN junction, which is going to act as a barrier between the N-type and the P-type. And then we have a tempered glass here. And we have in between the metal grids. So these metal grids are going to form one of the electrical contact of this diode. So this is one point of electric contact. And why they are used, why the metal grids are used? Because they will allow the light to fall on the semiconductor between the grid lines. So they are going to allow the sunlight to fall in between the grid lines. And what is the purpose of using this anti-reflective layer? Anti-reflective layer between the grid lines increases the amount of light transmitted to the semiconductor. So anti-reflective layer is going to increase the amount of light transmitted to the semiconductor. So one contact is metal grid. What about the back contact or the rear contact? It is another metal contact which is made up of silver. So this is about the construction. So we have N-type phosphorus doped silicon. We have boron doped P-type silicon. So phosphorus is a pentavalent, boron is a trivalent. Phosphorus being pentavalent, it has 5 electrons. So out of 5 electrons, 4 electrons will form covalent bond with 4 silicon atoms. What about the fifth electron? Fifth electron remains as an excess electron. So N-type has an excess electron. 5 electrons we have. 4 electrons will covalently bind with 4 silicon atoms. Silicon is tetravalent. So with 4 silicon atoms, 4 phosphorus electrons will bind. Fifth electron will remain as an excess electron. Similarly, in case of p-type, we have boron doped. Boron is trivalent. Okay, and this trivalent means 3 electrons will covalently bind with 3 silicon atoms. But we have 4th silicon atom also there. To bind a covalent bond in between the boron and the silicon, boron is not having one more electron. It is having only 3 electrons. 4th electron is not present. So that bond will become incomplete. Hence, a hole is created in p-doped silicon. So N-type, we have extra electron, and p-type, we have extra hole. Okay, so how is this going to work? So when light falls on this p-n junction, we have extra electron in the N-type. It wants to go and meet the hole which is present in the p-type. Electron and hole wants to unite with each other. They want to make a pair. But this is not possible because we have in between a p-n junction. Okay, which is due to this depletion region, the electron cannot bind with the hole. I mean, cannot pair up with the hole. At that time, what happens? Electron somehow it want to go and reach the hole. We have provided an external electric contact here, right? So this is a one-way path, one-way road. Only the electron can travel through this, but hole cannot travel like this. It is a one-way road. Electron can travel from here through the load, generate power, and then go and pair with hole. So electron hole pair recombination will take place, thus generating electricity. So how it is working? When light falls on the p-n junction, the free electron is ejected from the N-type. This electron want to meet the hole. But due to this p-n junction, due to the depletion region, it cannot pair up with hole. But it is very eager to meet this hole. So what it will do? We have provided an external conducting path, which is a one-way path. Only the electron can go through it and not the hole. So electron will travel through this one-way road, through the load, go and pair up with the hole, thus forming electron hole pair recombination, generating electricity. So this is how photovoltaic cell is working. Is it clear? So what are the advantages? So fuel source is vast. Yes, solar energy is infinite. And we are not using any kind of fuel, so operating cost is less. But however, installation cost is more. It is one-time investment. Okay, and it is not we are not conducting any kind of reactions here, so no emission or no combustion, which is going to lead to air pollution or the global climatic change. So it is not going to contribute to these kind of emissions or combustions or pollution, because we are not carrying any kind of harmful reactions here. And this is going to work at ambient temperature, and the installation can be done very quickly and environment friendly. As I said, we are not producing any kind of toxic products from this, so it is highly eco-friendly or environmental friendly, we can say. And heavy public acceptance. Yeah, everyone, we can see on everybody's terrace we have solar cells installed, right? So public has accepted this product, and safety wise it is excellent. So these are the advantages. Then what are the limitations? Definitely there are some limitations, there are some disadvantages. So as I said, installation cost is little bit high. And energy, when it can be produced, it can be produced only during daytime. So during cloudy kind of nature, it cannot produce electricity. During night time, when sun is not there, it cannot produce electricity. And sunlight is a diffuse source, that is, it is relatively having low density energy, and space is a constraint. Yes, space is required. If we want to install the series of this kind of solar panels, then we need space. Okay, so that is space required to generate unit power output is relatively more. If you want to generate more, we need to connect more, hence space is a constraint. So these are the disadvantages of photovoltaic cells. Okay, is it understood? Reply in chat box. Construction working and advantages and disadvantages of photovoltaic cell. Is it understood? Please reply fast. Somebody reply, yaar. Okay. So next one is another very, very important but little bit complicated topic. That is preparation of solar grade silicon by Union Carbide process, which will be asked for 7 marks. So I'm telling now only, this is little bit complicated, okay, to understand. I'll try my level best to teach it online. Let's see how best we can do. In case if you are not convinced, and if the meeting gets over, I'll reschedule it. I have to complete this today at any cost and make you understand. Okay, in case if we get disconnected, we'll reconnect and complete this until you guys understand this, because I said it's not just so easy to understand, because the reactions are little bit complicated. So please try to understand with concentration. Okay, so focus. So preparation of solar grade silicon by Union Carbide process. Actually, the PV cells or the electronic components or the semiconductor materials where we are using silicon, okay, they require silicon which is of 99.9999% purity. So they require highly purest form of solar grade silicon. And whatever the solar grade silicon of 99.99% purity, we are going to synthesize it by using metallurgical grade silicon. Metallurgical grade silicon is 98.5% pure. We cannot use that. Okay, so from 98.5% metallurgical grade silicon, we are converting it to 99.99%, that is ultra pure silicon. How? By using this Union Carbide process. Why the name Union Carbide? Because this method, Union Carbide process method, was introduced by a US based company, Union Carbide Chemicals. So Union Carbide Chemicals is a company which is located in US, has come up with this process where we can get or we can prepare the silicon which is of ultra pure quality. Okay, so let us start with that. Concentrate. So step 1. First we need metallurgical grade silicon. So I said metallurgical grade silicon is 98.5% pure. How do I get this 98.5% purity silicon first? So take the quartz. This is easily abundantly available in nature, that is in the form of SiO2. Treat it with carbon. So I want silicon from this. Means I want to remove the oxygen. How do I remove the oxygen? By doing the reduction. How do I carry out the reduction? By using carbon, heating this at extremely high temperature of 1500 to 2000 degrees centigrade in an electric arc furnace. Then only we can reduce this. So in an electric arc furnace at very high temperature of 1500 to 2000 degrees centigrade, in presence of carbon, I'm going to heat this quartz. Then I'm going to get a liquid silicon with the liberation of carbon monoxide. So this liquid silicon which is obtained, it is having some kind of impurities in it. Impurities in the form of aluminium, calcium and magnesium. So I have to remove these impurities also. So how do I remove them? That can be removed by treating this silicon which is having the impurities with oxygen and silica. Okay, so I have to treat it with oxygen and silica. Thereby these will undergo oxidation. Aluminium, calcium and magnesium will form their oxides and the product finally obtained is called as slag, 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 that can be removed by gravity or mechanically. So aluminium, calcium and magnesium oxides in the form of slag which is formed are removed mechanically or by gravity. And what remains? We remain with silicon, and thus obtained silicon is of 98.5% purity, that is metallurgical grade silicon. Let me repeat again. So let us take quartz, treat it with carbon at temperature of 1500 to 2000 degrees centigrade in an electric arc furnace, so that this will get reduced and we get liquid silicon. But it does contain some of the impurities in the form of aluminium, calcium and magnesium. In order to remove these impurities, I'm going to treat the mixture that I have got using oxygen and silica. So once I do that, all these are undergoing oxidation. So they'll form the oxides like Al2O3, CaO, MgO are formed. And thus the obtained product is called as slag, which can be removed by gravity or by mechanically. And once they are separated, what remains is silicon. So that silicon is metallurgical grade silicon. I hope this point is clear. Next, using metallurgical grade silicon, we are going to produce solar grade silicon. How? So take that metallurgical grade silicon, treat it with dry HCl gas at 300 degrees centigrade. So we'll get two products. One is trichlorosilane, another one is tetrachlorosilane. I got a notification that only 9 minutes is remaining. In case if it gets disconnected, we'll reconnect because we have to complete this. Okay, so take the metallurgical grade silicon, treat it with dry HCl at 300 degrees centigrade. So we get the major product as trichlorosilane, and with a little bit or a small amount of tetrachlorosilane. Why trichloro? Cl are 3. Okay, chlorine are 3 here, so it is called as trichlorosilane, and here they are 4, so it is called as tetrachlorosilane, tetra 4. Okay, now whatever this trichlorosilane is obtained, okay, that is subjected to distillation. But this tetrachlorosilane is there, right? We need to convert it to trichlorosilane because it is having 4 chlorine. We don't want that. We want tetrachlorosilane to be reduced to trichlorosilane. So how do I reduce it to trichlorosilane? By treating it in a hydrogen reactor at 1000 degrees centigrade, so that tetrachlorosilane gets converted to trichlorosilane. So I got already trichlorosilane, and this tetrachlorosilane also I converted to trichlorosilane. So obtained mixture is purified and then it is subjected to a fixed bed column. So this is the first column, first fixed bed column, which is having a catalyst called as quaternary ammonium ion exchange resin catalyst. So this catalyst is going to convert trichlorosilane to dichlorosilane. So trichlorosilane is reduced to dichlorosilane in presence of this catalyst in this fixed bed column. But see here, we got again one more product, that is tetrachlorosilane. So this tetrachlorosilane, what I will do? Again, I will convert it to trichlorosilane, and again I will convert it to dichlorosilane, so that this will not be wasted, so that I can get silicon from this also. Okay, so tetrachlorosilane, how do I convert it to trichlorosilane? In hydrogen reactor at 1000 degrees centigrade, so that I'll get trichlorosilane, and then it is again passed to this fixed bed column containing the catalyst, so that even this is converted from tetra to tri and then to di. Okay, tetrachlorosilane is converted to trichlorosilane, and then trichlorosilane in this presence of this catalyst is converted to dichlorosilane. Now the products are separated by distillation. Okay, what happened? Are you able to see the screen? Sorry, there was some error. Okay. So this dichlorosilane, whatever we got, this dichlorosilane is now passed to second fixed bed column with the presence of the same catalyst quaternary ammonium ion exchange resin. So now dichlorosilane is converted to silane, that is SiH4. Silicon is 4 times covalently bonded with hydrogen, with 4 hydrogen. It is having 4 hydrogen with covalent bonds. Okay, and again I have got trichlorosilane here. So this trichlorosilane will again go for the back process, where in this first big bed column, where again it is converted to dichlorosilane, and from dichlorosilane to silane. So this side product, whichever is going to obtain, that is going to the previous steps. Okay, you do remember those steps. So we are interested in the silane now. So the silane which is obtained has to be converted into silicon. So how do I convert it into silicon? It is in the form of SiH4. I have to break the hydrogen bonds. How to break the hydrogen bonds? By undergoing it to a pyrolysis reaction. Pyrolysis means heating it at extremely high temperature in a metal bell jar reactor, so that all the bonds are broken and we get silicon plus 2H2. Thus obtained silicon is called as solar grade silicon or polysilicon, okay, which is of 99.9999% purity. Ultra pure silicon. Why it is called as polysilicon means in that crystal we have several ultra pure silicons together, hence the name polysilicon. So in that crystal, okay, it is in the form of crystal. Okay, is it understood? I'll repeat again. Please concentrate. So I have metallurgical grade silicon. It is treated with dry HCl at 300 degrees centigrade. So we'll get two products. One is the major product trichlorosilane. Another one is a small amount, that is tetrachlorosilane. Tetrachlorosilane has to also be converted to trichlorosilane, so that let us not waste this. So how do I convert tetrachlorosilane to trichlorosilane? In a hydrogen reactor at 1000 degrees centigrade. So once I treat SiCl4 with hydrogen, I'll get tetrachlorosilane. So here also trichlorosilane is there. Here also trichlorosilane I have got. The products are distilled, purified, and then they are passed into first fixed bed column. Okay, this is first stage. And here we have the catalyst called as quaternary ammonium ion exchange resin catalyst. So this is going to reduce trichlorosilane to dichlorosilane. We are interested in dichlorosilane. However, let us not waste this tetrachlorosilane. Tetrachlorosilane, again you send it to hydrogen reactor so that it will form trichlorosilane. Again from trichlorosilane, you send it to the first bed column so that it will form dichlorosilane. So those previous steps you have to remember. Okay, now. So this dichlorosilane which is obtained, okay, it is again passed to second bed column, which is also containing the same catalyst quaternary ammonium ion exchange resin, wherein which this dichlorosilane is converted to silane, in which we have silicon bonded with 4 hydrogen. And again, I have got trichlorosilane. Trichlorosilane, you send it to first fixed bed column so that it is converted to dichlorosilane. Dichlorosilane, again, you convert it into silane by sending it to second fixed bed column in presence of catalyst. So this part is the previous back steps. Okay, I have got silane now. So this silane has to be broken so that I'll get silicon. How do I do that? In a metal bell jar, by subjecting it to pyrolysis reaction, that is heating it at extremely high temperature so that the bonds are broken and we get silicon, which is of ultra pure quality in the form of a polycrystalline silicon. Okay, so this is the one which we are in need of, which is of 99.99% purity. I hope you understood now. Is it clear, students? One second, I'm taking the attendance. Yes, please mention, did you understand this process? Is it clear? Just you have to remember these reactions, okay? 1, 2, 3, 4. 4 reactions. And explanation is very simple. Treat it with HCl to reduce it, treat it with hydrogen in hydrogen reactor, and conversion means we need a catalyst, that is quaternary ammonium ion exchange resin catalyst. Same process here also. And from silane to silicon, it is pyrolysis reaction. Okay, heating it at extremely high temperature so that the bonds are broken and we get silicon with hydrogen. And this silicon is of ultra pure quality. So this is what you need to answer if they ask the question for 7 marks. Okay, so this completes module 3. Next we will start with module 5 from Monday. Okay, did everyone understand? Fine then. Thank you.